So condition number one, what you see is one end is fixed. So I'll write here, one end fixed. Right? And the other is what we call the free end. Like how this beam has been held. Okay. So the equivalent length, LE, okay, so LE, right? So this is our LE. Right? The equivalent length right? So LE, as you can see, is equal to 2L. Okay, right? It's equal to 2L. Now we are going to apply what we have done so far. So based on, so what does it mean, 2L? What does it mean to us physically? Okay, so we are going to base on what we have done before. So based on critical stress of 250, like what we have before, times 10 to the power 6. And based on Young's modulus, is equal to 200 times 10 to the power 9 Pascal, right? So we know that the formula is L over R is equal to square root, right, of pi squared E over, not E, it is, E over stress allowable, right? Okay. So now our E, our L, right, is equal to what? 2L due to what? Due to one end free and the other fixed, right? When that's the case, you let this be equal to what? 2L R. So this will be equal to pi squared 200 times 10 to the power 9 divided by 250 times 10 to the power 6. So therefore, your L over R now becomes what? So L, so we have, initially we have what? We have 88.86 divided by 2 is equal to 44.43. Okay, now this is equal to 44.43. Now what does this actually mean? Okay, so I'm going to copy this graph over here. Okay, and I'm going to paste over here, get rid of some stuff. So physically, what does it mean? Now, right, based on how it's fixture, the L over R ratio now is 44.1. It's equal to 44.43. So 44.43, I'm going to eyeball this, okay? 44.43 is somewhere around here. Okay, this is our, yeah, halfway sounds good. Okay, so over here now our value is what? 44.43. Okay, so I'm going to draw in red. So now it will go flat and then it will reduce after 44.43. Okay, so again, what it means, so for this structure over here, this end you just need to do stress is equal to P over A, or deflection is equal to PL over AE, right? On the right hand side, now you have to consider what? So what I'm trying to say is this: if you have a structure that, so what? Okay, rather than me trying to tell you What do you think about this? Is the structure more likely to buckle or less likely to buckle? More likely, yes or no, right? The L over R ratio is so bad now, right? The L over R ratio is 44.43. So if we have the same example like we had before, where L, right, where if we have our R, if R is equal to 0.356 meters, right, our L will be equal to 44.43 multiplied by 0.356. So this will be equal to 44.43 multiplied by 0.356 is equal to 15.817. So if your structure has a length of 15.817 and greater, failure will be due to what? Buckling. Okay. So this is what we call the extension of Euler's formula. And it's true, right? If a structure loading this way, the tendency for it to buckle is much higher. Like what I did just now with a piece of paper, right? One end is free, the other one is built in. It's not nearly built in, but it's more or less, I'll call it pin, because it will not resist any moment. Then your LE value will change. Okay. Now let's look at another condition. Okay. Let's look at condition number 2. So condition number 2, right? So our okay. Condition number 2 is both ends are thin. Okay. So if this is my x-axis or my y-axis, and this is our x-axis, right? We know that when x is equal to 0, y is also equal to 0. When x is equal to L, y is equal to what? 0. Okay. So this looks familiar, right? This boundary condition looks familiar, right? So you can see it has what? Pin ends. Now, how are pin? So let's look at this one. These are pin ends. So as you can see, pin ends, if you look at pin ends, okay, it means that you allow linear motion in one direction. For this case, okay, in one direction. Right? And allow rotation. Okay, and you allow rotation. Okay, so this is pin end. The previous example over here, right? The previous example is what? Fixed end. So pin end and fixed end are different. Okay, it means what? When it's fixed end, no rotation is allowed. Okay, and also no linear movement. Okay. So coming back to our problem over here, for this case, the equivalent length is equal to L. It's exactly as the same thing that we derive. Okay, so if I were to bring this up, okay, if I were to copy this entire graph, Okay, we don't need to do anything. It's exactly this condition. Okay. So i.e., if we have a laudable stress of 250, right, and if the material is steel with 200 gigapascal of Young's modulus, this is our graph. Okay. So the next one end is pin. Okay. The third condition number 3, is where one end is fixed end and the other end is one pin end. Okay. So one you can see is built in, right? It's fixed, so this side is a fix, and the other side is a pin end. So you still allow rotation. Okay, you still allow rotation. So when that's the case, the LE is equal to 0.7 L. Okay, so if 0.7 L over R is equal to 88.86, the L over R ratio now increases. So it's 88.86 divided by 0.7 is equal to 126.9. Okay. So for it to buckle, right? So let me copy this graph again. Let me copy this graph again. So now, right, our stress critical or our L over R ratio extend to 126. Okay, so as again, I'm going to eyeball this at 126. Okay, so 126 is about here. Okay. So this is our 126.9. So it means our material is more resistant to buckling now because of the way it's fixture. Okay, come on, Eugene. So it's straight up to here, and then it will release itself. So for this case, you have to do buckling analysis. Over this end, you just do stress is equal to P over A, or deflection is equal to PL over AE. Okay. And then condition number 3, these are the condition number 4. These are the 4 most common conditions. So condition number 4, before we stop, is where we have a condition where where both ends are fixed. Okay. So in this case, the LE is equal to 0.5 L. Okay. So the L over R ratio now is equal to what? 177.7. Right. So it's so much more resistance to buckling. So if I were to just copy this again, just to show. Okay, now you guys know how this graph works. It's straightforward. Okay. So now what happens now is 177. So if this is 180 over here, right? 177 will be somewhere around here. Somewhere around here. So the graph will stretch on and then, okay. So again, buckling. And over this side, you use stress is equal to P over A, or deflection equal to PL over E. Now the thing is this. How did they determine the equivalent length? Anyone? How do they know that, okay, when it's done like this, LE is equal to 0.5? When it is one end that is fixed, the other end is free to, is pin, is LE is equal to 0.7 L. Anyone? Due to time, a lot of experimental work has been carried out. It's based on what? Experiment. Okay, that's why it's based on experiment with different material, right? Different length, different radius of gyration. They get this. It's a lot of data. That's what you're going to learn in 3E05. Okay, how to use data. Okay, to calculate things like the equivalent length. 3E05, that the course that you're going to do next has a lot on this aspect. Okay, before I stop, I'm going to talk to you all about